Welcome back on the class of Introduction to Solid Mechanics. So I hope you all are safe and doing well. So in the last class we have seen the slope and deflection, and in the slope and deflection I have discussed three theorems, that is Maxwell reciprocal theorem, superposition theorem and Bette's law, and we have seen the scope of that theorem. So I told you in the last class that superposition theorem, that is very important for the competition point of view like GATE exam and engineering services exam. And we have seen the for different various loading, we have computed the value of individually, we have computed the deflection and slope and just superimpose all the deflection and slope, and we have computed the deflection at given point. So today I am going to discuss another topics in the introduction to solid mechanics, that is shear stress in the beam. So in this chapter I will discuss the expression of shear stress due to the shear force acting on the beam, and after that maximum shear stress and normal average shear stress we will compute, and the distribution of shear stress for various cross section like in rectangular beam, in circular cross section, in triangular beam and in a prismatic beam. So let us take a beam . And a section having width is B and depth is small d, and let us assume this is neutral axis, and I have taken this section. From this distance it is y, and this is dy. Two sections I have considered, x1 and x2, which is as a distance of dx. This is x, A, B, and a load is acting capital P. So we can compute the moment at x1. So m x1 is Va into x, and m x2 is Va into x plus dx, where m x2 is greater than m x1. According to bending equation, bending stress is equal to m into y by I. So we can write bending stress at x1 is sigma x1 is m x1 into y divided by I. So due to this shear force, a shear stress will also act. Let us assume this is fx1 and this is fx2, is nothing but sigma x2 into dA, stress into area. This is dx. So a shear stress will act, and the magnitude of shear stress is tau into B into dx. This is B. So sigma x2 is nothing but m plus dm divided by I into y. dm is nothing but Va into dx. So summation of forces in x direction, so fx1 plus shear stress tau into B into dx is equal to x2. So tau into b into dx is equal to m plus dm by I into y minus m into y by I into dA. So tau into b into dx is dm upon I into y into dA. So tau is equal to dm by dx into y into dA divided by I into b. So we know dm by dx is shear force. So tau is equal to v in upon ib into y into dA. So shear stress is v upon ib into y into dA is ay bar, moment of area, where v is the shear force at the section where shear stress measured. I is the moment of inertia of cross section about neutral axis, and b is the width of cross section at that point where shear stress measured. And similarly, A is the area of the point above or below where shear stress measured, and y bar is the distance of centroid of above area from the neutral axis. So this is the expression of shear stress. Tau is equal to V by IB into AY bar, where V is the shear force at that section where we have to compute the shear stress, and I is the moment of inertia at that cross section, and B is the width of the cross section at that point where shear stress measured. A is the area of the point where shear stress measured, and Y bar is the distance of centroid of above area from the neutral axis. So with the help of this, we can compute the value of shear stress at any point. So dear learner, I have derived the expression of shear stress at any cross section, and the expression is shear stress is tau is equal to V by IB into AY bar, where V is the shear force at that section, I is the moment of inertia where we have to compute the shear stress, and A is the area of the cross section at that point where we have to compute the shear stress, and Y bar is the distance of CG from the neutral axis where we have to compute the shear stress. So after that, I am going to discuss what is the magnitude of maximum shear stress occur in that cross section, and what is the expression of average shear stress, and what is the expression of shear stress at the neutral axis. So for different cross section like rectangular cross section, triangular cross section, circular cross section, I section, T section, we will see how to compute the value of shear stress and maximum shear stress. So firstly, I am taking rectangular section. In rectangular section, we will see the expression of normal shear stress and average shear stress and maximum shear stress, and also we will see what is the position at which point this maximum shear stress occur and the distribution of shear stress I will show you. So let us take a rectangular section having the width is capital B and depth is small d. So we know the neutral axis of this rectangular section, that is at a distance of d by 2 from the top or bottom. I have taken a section at a distance of y from the neutral axis, and the CG y bar is this one. This is the area where we have to compute the expression of shear stress. So we know the moment of inertia is I is equal to B dq by 12, and the expression of shear stress is tau is equal to, expression of shear stress is V upon IB into A y bar, where V is the shear force at that section where we have to compute the shear stress, I is the moment of inertia of that section. So firstly I will compute moment of area A y bar. So what is the area? So I have taken this section, so area of this section is how much? This distance is d by 2, this is d by 2 and this is y, so this one is d by 2 minus y, so area is B into d by 2 minus y, is capital B, into y bar. So y bar is how much? Y plus d by 2 minus y by 2. So y bar is y plus d by 2 minus y divided by 2. So ay bar is coming capital B into d by 2 minus y into, this is 2y minus y, so y plus d by 2. So ay bar is B into d by 2 plus y into d by 2 minus a plus b into a minus b, it is a square minus b square. So d square by 4 minus y square divided by so it is coming this one. So it is coming b by 2 into d square by 4 minus y square. So shear stress tau is V upon I into B A y bar. So the expression of shear stress is V into A y bar is B into d square by 4 minus y square divided by 2 into B into dq by 12 into B. So B cancel. So it is coming shear stress tau is 6V by B into dq d square by 4 minus y square, or we can write in terms of moment of inertia. So shear stress, we can also write in terms of moment of inertia. So shear stress tau is V upon 2I d square by 4 minus y square. So we have seen the distribution of shear stress is parabolic because this is 2-degree equation. So the maximum shear stress, when maximum shear stress occur when y is equal to 0. So maximum shear stress occurs at y is equal to 0. That is at when y is equal to 0, that is at neutral axis. So at neutral axis. So when y is equal to 0, so expression is 6v by b dq into d square by 4. So maximum shear stress, tau max, maximum shear stress is nothing but 6v by b dq into d square by 4. So it is coming 3 by 2 d square cancel, v by b into d, and the v by bd is nothing but v by bd is nothing but average shear stress. Average shear stress is nothing but shear force divided by area of that cross section. So area of that cross section is bd and the shear force acting at that section is v. So this is average shear stress in a rectangular beam is shear force divided by area of that cross section. So maximum shear stress is equal to 3 by 2 into v by bd, and v by bd is nothing but 3 by 2 into tau average. So the maximum shear stress is 1.5 times average shear stress in a rectangular beam. As I told you earlier, the variation of shear stress is parabolic. So if I draw the shear stress distribution for a rectangular beam, this is the neutral axis, and at neutral axis maximum shear stress occur. So if I draw the shear stress diagram, expression of shear stress, let me write. So it is 6v by b into dq d square by 4 minus y square. So when y is equal to d by 2, this is d and this is width b. So this is neutral axis. So when y is equal to d by 2, shear stress is, when y is equal to d by 2, shear stress is equal to 0. So when y is equal to d by 2 or minus d by 2, it is 0. When y is equal to 0, it is occur maximum shear stress. So the variation of shear stress we can draw like that. So the maximum shear stress is occur at the neutral axis. This is tau max and the distribution is parabolic, the maximum shear stress. Now I am interested to compute the distance from the neutral axis where average shear stress is equal to the normal shear stress. So this is the distribution of shear stress when y is equal to 0, tau is equal to tau neutral axis is equal to tau max is equal to 1.5 times tau average. So in rectangular section, maximum neutral axis occurs at the neutral axis and the magnitude of that maximum shear stress is 1.5 times the average shear stress occurs in the rectangular beam. So we can write maximum shear stress in a rectangular beam occurs at neutral axis and magnitude of maximum shear stress is 1.5 times the average shear stress. So if this is the maximum shear stress, at any point where the average shear stress is also there, this is the distribution of average shear stress, and this value is V by B into D. So we have to find that point where this average shear stress will equal to the normal shear stress. So normal shear stress is equal to average shear stress. So normal shear stress is how much? It is coming, normal shear stress is 6V by B into dq, d square by 4 minus y square, and average shear stress is V by B into D. So V cancel, B cancel, so 6 by d square into d square by 4 minus y square is equal to 1. So d square by 4 minus y square is equal to d square by 6. So y is equal to y square is equal to d square by 12. So y is equal to d by 2 root 3. So this is the distance from the neutral axis, where so at y is equal to d by 2 root 3 from the neutral axis, average shear stress is equal to normal shear stress. So if this is a rectangular section and this is the diagram, we have seen the distribution of shear stress. This point is maximum shear stress, this is maximum, tau max. So at a distance of this distance and this distance, so this distance where normal shear stress and average shear stress is equal, that is d by 2 root 3, and this is also d by 2 root 3. So this is the distribution of shear stress in rectangular portion, and we have seen the expression of shear stress in rectangular section, that is 6V by B dq, d square by 4 minus y square, and average shear stress is B by BD, and maximum shear stress occur at the neutral axis. So dear learner, today we have seen the expression of shear stress, and that is V by IB into AY bar, and after that I have taken a rectangular section and we have seen how this shear stress will vary. So we have seen the expression of shear stress in rectangular section, that is 6V by B dq into d square by 4 minus y square, and we have seen this expression, this shear stress will vary parabolically, and maximum shear stress is occur at the neutral axis where y is equal to 0, and this maximum shear stress will occur at the neutral axis. That's why it is also called shear stress at the neutral axis, and the shear stress is neutral axis is exactly equal to the maximum shear stress, and the magnitude of maximum shear stress is 1.5 times the average shear stress in a rectangular beam. So average shear stress is nothing but the shear force by the area of that cross section. So average shear stress in the rectangular section is V by BD. So maximum shear stress is 1.5 times V by BD. Similarly, we have seen the distribution of shear stress in the rectangular beam. So when y is equal to exactly d by 2, so shear stress is coming 0, that is at the top compression and top compression fiber, the shear stress is coming 0. Similarly, when y is equal to 0, shear stress is coming maximum shear stress. So the entire distribution we have drawn, so it is coming parabolically and maximum shear stress occur at the neutral axis. So in the coming class I will discuss another distribution of shear stress in the I section, circular section, triangular section, and we will see the maximum shear stress occur at which point. Take care of your health and happy learning.